So in this video, I'm going to motivate the idea of one interesting aspect of computer science, the union find data structure. I'm just going to motivate the idea in this video, and in the next one I'm going to get into a lot of detail. But in this video, along with the motivation, we're going to use this structure to solve for the clustering problem, right? And you're going to just look at this very beautiful union find data structure. So what is the purpose of this data structure that I'm going to implement? Once upon a time, somewhere in the world of theoretical computer science, there was a set of objects, and what one scientist wanted to do was maintain some sort of a partition, some sort of a set of this set of objects, some sort of a partition in this set of objects. That's all he wanted to do. He wanted to maintain a partition in this set. He wanted to be able to find an object, for example, find some object returns in which partition do I belong. I want to union two sets Ci and Cj and return one single union, so to speak. That's why the union find data structure. I mean, there is only two operations, union and find, and the scientist thought, well, what should I name it? Let's name it, instead of find union, I would rather name it union find, because he thought of doing union first. So why are we talking about this data structure? Well, if you have seen my kruskals video, which I recommend you do, this comes very handy when doing kruskals problem, kruskals minimum spanning tree. For example, what I will start with, n partitions, each partition representing one node in my graph, right? And as and when edges are added, I start unioning these partitions. So whenever the first edge is added in my kruskals algorithm, I union those two nodes into one single node. And as the kruskals algorithm goes on, this partition slowly from n, it becomes n minus 1, then n minus 2, and slowly it goes to 1. And it's also very important, very easy to see how this will help you check for cycles, which was needed in the kruskals algorithm. For example, if one node is in partition A, another node is in partition B, as these both partitions are different, adding this edge will not create a cycle, which we even proved when we were doing kruskals algorithm. But if one node is in A and another node is also in A, adding this edge will create a cycle somewhere across this through this particular partition. So I'll find a node x1, and I'll find a node x2 in my union find data structure. And if these both are equal, that means there is a cycle when I merge these two, and hence I will skip this step. I will only merge the two sets. I will only merge two partitions where their finds are not equal, right? So this is very straightforward in seeing how this is really helpful in kruskals algorithm. And if you don't understand this, I encourage you to go and watch that video. But we're going to discuss about the union find data structure in much detail. One thing is really interesting is, let's try to analyze this data structure. Let's see how we can maintain it and how we can do cycle checks in, let's say, constant time. So here's one idea that I have. I'm just going to start brainstorming some ideas with you. For every node in a particular partition, for every node I can maintain a pointer to its leader vertex. So for example, I have this graph x, y, z. This is one particular partition. So another idea number 0, if I may. idea number 0 is to maintain one single linked structure, one structure per partition, one structure, one singly connected complete structure per partition. Idea number 1 then will be to maintain a leader vertex. So x points to itself, z point to x, and y points to x. So whenever I ask find z, whenever a user comes to me and says find z, and then he says find y, what I have to do is go to z, traverse its pointer vertex to its leader pointer vertex. I come to x. Whenever the user comes to me and says find y, I go to y, transfers its pointer vertex, and I come to x, and hence I result that this is equal to x and this is also equal to x, and the user will do whatever he wants to do with this, but this is how my idea is. Another example, suppose I have another graph, let's say u v w whatever, and then again my u is my leader vertex that I have decided arbitrarily, and so every vertex points to its leader vertex in its connected component, in its partition. For example, this was C2 from our this diagram, this one was C2 and this one was, let's say, C1. So every vertex points to its leader vertex, every vertex points to their leader vertex in their component, so that find operations take only constant time, that is transversing one pointer vertex. So name of the component, for example, I have given here C1, I have given C2, C3, C4, C5, C6. In this case, the name of my component will be whatever the leader's name is. So that's very that's a natural idea to do, and in this can very easily be seen to help with kruskals directly. So given an edge uv, that is, we are trying to see if adding uv to a minimum spanning tree creates a cycle. Well, it's very easy. Find u, find v. If they are equal, that means they both are in the same connected component in our union find data structure, and hence if you add edge uv to our MST, it will create a cycle. So skip this entirely. So order 1 cycle checks. But here's the next question that a good YouTube viewer will ask. For example, let's say find u is not equal to find v. So in that case, add edge uv and union the c corresponding to u and the c corresponding to v. I mean the component corresponding to u and component corresponding to v. So what I have to do now in the back end, in the background, is go to whichever I'm merging and change all of the merged components. For example, if I'm merging u with v, all of the vertices in u now point to its leader vertex. Now they have to point to v's leader vertex, and then so whenever I'm doing a union, I have to update a lot of pointers to reflect this new unionized c of, let's say, alpha, right? So the question is, how many pointer updates are needed? So, well, I come to another idea. How many pointer updates will I ever need? If that's my question, if I say so myself, like in the entire running of the algorithms, how much work do I have to do to update these so-called pointers? So here's the idea. Whenever a union operation is run, merge the small set into the bigger one, small set into bigger one, into the bigger one. Well, this is very simple, very a very natural idea. Like, why should I ever update pointer vertexes of the set which is bigger? That makes no sense. Why do more work when I can do less? I will always whenever I'm doing a union operation, I'll see the cardinality of this set, and I'll see the cardinality of this set, and if this is greater than this, if the cardinality of set A is greater than the cardinality of set B, I will only update vertices from set B. Okay, that is for sure making sense to you, and that is also correct in its case. I mean, instead of choosing them arbitrarily, I will choose whichever is the one which is smaller. So here's the question again: how many pointer updates are needed? Let's think in terms of each vertex. For example, you are a vertex in this entire universe, floating by yourself. First of all, you were pointing to yourself because it was that's the way it was initially, but then you got merged to someone just because you were alone and they were maybe not alone, so you got merged to someone. Now you are at least with somebody else in your clique, in your component. Now only when you are smaller than somebody else, you as a vertex alpha here, only when you are smaller than someone else, you are merged. So now that you are at least 2, only when someone else is bigger than 2, your pointers are updated. Now you are at least 4. Now only when somebody else is at least 4 does your pointer gets updated. Now you are at least 8. So do you see what I'm trying to go to here? I mean, you can only double in size. You at least double in size, right? Your entire component at least doubles in size. So now that initially you were 1, then you got merged with someone, you were at least 2, then you got merged with someone, you were at least 4, then you were merged with someone, you were at least 8. So how many times can this happen? This can only happen log n times. That's what I am saying. For every vertex, the update can only happen at max log n times. For example, if the vertex was so unlucky that every time the vertex was in the smaller partition, the one which was getting merged, the vertex was in the smaller partition. For example, you were so lucky that you were so unlucky that each and every union operation puts you in the smaller one. Even then, your pointer will only get updated log n times. Each vertex at max has log n updates. So all of the n vertices at max have n log n updates. So that much work I have to do while running through the entire algorithm, n log n. From the broader perspective, each individual vertex may be different, but as a whole, as an entire universe, when I'm talking about the entire universe, at max you are doing n log n work. So whenever you are unionized, your new cardinality, your new population is at least greater than twice your old population, right? Because if you were in the smaller one and your vertex pointer gets updated, you are going to get doubled, that's for sure. But because you were in the smaller, let's say 2 more vertices in the other one, and that's why you were smaller. So that was 2n plus 2. So always greater than equal to 2. That's what I'm saying. Whenever your pointer is updated, you are always going to be greater than equal to 2. That can only happen a max log n times. So for all of the vertices, if I go to log n times, at max it's going to be n log n. The entire union operation is going to be n log n. So for the entire kruskals algorithm, it's going to be order m log n for sorting the edges, order m for cycle checks, for cycle checks for O1 per edge, and order n log n for this unionized operation, right? So instead of taking a vertex centric view, I'm taking the global universe centric view. So can we do better is the question. Can I do better than this? I mean, I really don't like seeing this n log n here. This is bugging me. I also want to do cycle checks in a constant time, and I don't want to spend so much time merging. So yeah, I can do better. OM, order of m by 2 randomized, if I am doing randomized, and randomized turns out to be one of our helping hands, when doing some complex algorithm analysis. or I can do order m alpha n, where alpha n is the inverse Ackermann function. We're going to get into this in part 2 of the video, in the second advanced version of the video. I can only save you some time and give you some idea of what inverse Ackermann function is. Inverse Ackermann function is slower, or I mean faster, so to speak, is lesser than log star of n. Log star of n. So if log star n was like this, inverse Ackermann function would be like this, you know. So it's lesser. So in computer science terms, this one is faster than this. And what is log star n? Log star n is take a number n, apply as many times as needed, apply log to it, that this becomes less than 1 or just 1, for example. So log star of n, it's a very insane thing to think about. Log star of n is basically the inverse of 2 raised to 2 raised to 2 raised to 2 raised to 2 to n times. Basically that's how it is. So apply log as many times as needed to get this value less than 1. And think about it, for a number as greater as, let's say if I take 1000, log star of n will be 1024. I put one log into it, it becomes 10. I put another log into it, it becomes 3, I guess, 3 point something something. I put another log into it, it becomes less than 2, for example. I mean 1, somewhere between 1 and 2. So log star of 1024 is going to be 1 2 3 is equals to 3. And you can just by adding one more number to this, I don't think the number is going to increase tenfold. I mean, this function is something that's going to bring down a number really fast, because that's how log is. So anyway, we'll get into it in much detail later, but now you understand what union find data structure is. I want you to forget each and everything you saw here. All I want you to remember is this diagram, and all of these ideas is something which I think you can get to naturally just if you think about it for a few minutes. All union find data structure does is, what's its reason of existence, what's its raison d'etre? Its raison d'etre is it maintain a partition of elements in a universe. That's it. Its operations are supported operations are find x, find which partition in this universe a particular x belongs, and then union to partitions, so to speak. And that's pretty much it. That's about the unified data structure. We will get into much more detail in part 2.